After studying this module, you shall be able to find reducible representations for various point groups by taking number of examples of the molecules and taking 3n coordinate vectors as the basis. You will be also know to find out or how you can use the bond vectors as basis for finding reducible representation. You will learn the examples for these two also. You can know also the p orbitals and d orbitals as the basis for functions. But in this I will just concentrate on few examples and for finding the reducible representation directly. We have learned the need for reducible representation, how to find out reducible representation without finding the matrices. Character for unshifted atom was explained by taking unit vectors along xyz axis, and these results were summarized in the table. For reference, in this module we will use that method and develop reducible representation for various point groups. We will look other bases also for finding reducible representation. Characters for various symmetry operations using 3n coordinate vectors are given as chi is equal to 3, chi I is equal to minus 3, chi sigma is plus 1, chi C2 is minus 1, chi C31 or chi C32 is equal to 0, so on, and for chi Cn is given as 2 cos theta plus 1, chi Sn is equal to 2 cos theta minus 1. Now we will make use of these characters and develop the reducible representation. And for starting, let us again take the very simple example of water molecule. How many atoms water molecule has? It has 3 atoms, oxygen, hydrogen and hydrogen. Now let us follow the procedure and see how many atoms are shifted. Now if I carry out E operation on this, E operation on this means I am not doing any work on this molecule. All the 3 atoms are not shifted. All the 3 atoms are not shifted. Now what happens if I perform C2 operations as shown into the diagram? That is, C2 axis is along this. It is like this. C2 axis is like this. And I perform a C2 operation like this. This is C2 operation like this. What happens? These hydrogens, they are interchanged or shifted, and only this oxygen atom remains at the same place. It is unshifted. So by performing C2 operation, only one atom is not shifted. Now what happens if I take sigma yz? That is, my molecule lies into this plane. All the atoms remain at the same place. Oxygen and 2 hydrogens, they do not shift. That is, all the 3 atoms are not shifted. Now what happens if I take sigma xz? This is my sigma xz bisecting HOH angle. Again here, this hydrogen and this hydrogen, they are interchanged, and the middle oxygen remains same. So by performing the symmetry operation corresponding to the water molecule, what I have learned? By performing E operation, all the 3 atoms, they remain same. By performing C2 operation, only one atom is unshifted, and by performing sigma yz, only all the 3 atoms are not shifted. By performing sigma xz, only oxygen atom is unshifted. These results are given over here in the form of table. That is, unshifted atom is 3, 1, 1 and 3. 3 under E, under C2 it is 1, under sigma xz is 1, and under sigma yz it is 3. by this meter. Now I multiply these unshifted atom by the character of the 3 Cartesian coordinates if I am taking 3 Cartesian coordinate as a basis. For E, what we have learned, it is character for 3 vectors is 3. So 3 into 3. Let us go to the C2. Only one atom is shifted. I multiply with minus 1 because the character for C2 when I take 3 vectors as the basis is minus 1. So 1 into minus 1. Sigma xz, unshifted atom is 1. And what is the character for sigma xz? When I take 3n vectors as the basis, it is plus 1. So 1 into plus 1. Similarly, sigma yz, here 3 atoms are unshifted and 3 atoms are unshifted. These are multiplied with plus 1. And the net result is 9 minus 1, 1 and 3. And this is represented as tau 3n. Tau is the symbol for reducible representation or representation in which 3n specifies that 3n vectors have been taken as the basis. Just what we have seen, just by simply noting how many atoms are unshifted and how many atoms are shifted, multiply with them the character corresponding to E, C2, sigma xz and sigma yz, in which we have taken 3n vectors as the basis, we can directly get the tau reducible representation. This is the example of water molecule. Let us take another simple example of that is C3V point group. Now this is my C3V point group. And in this how many symmetry operation you have? E, C31, C32 and 3 sigmas, sigma V dash, sigma V double dash. And now we have to see the effect of these 6 symmetry operation on these. How many atoms in these molecules? I am having 4 atoms, nitrogen, hydrogen, hydrogen and hydrogen. And I have to see how many atoms are shifted. Let us perform C3 operation around this axis, that is like this. So how many atoms are shifted? All the hydrogens are shifted and the nitrogen is not shifted at all. Similarly, by performing C32 operation, that is carry out C3 2 times, all the hydrogens will be shifted and the nitrogen will not be shifted. Now let us see the effect of sigma H. Sigma H, if I take this one, that is, it contains one of the bond and bisects the angle between other two. It has this one, it has this one and it has this one. So there are 3 sigmas. If I take like this, how many atoms are shifted? That is this and this, they will be shifted and this will not be shifted because it lies into this. So by performing sigma on this molecule, 2 atoms are not shifted and 2 atoms are shifted. So like this, by performing all the symmetry operations of in this ammonia molecule, we have seen how many atoms are shifted and how many atoms are not shifted. And the results again are given into the table of C3V point group. First row shows unshifted atom. E, all the 4 atoms are not shifted. C3 or C32, only 1 atom, that is the nitrogen, is not shifted. 3 sigma V's, only 2 atoms are not shifted, that is nitrogen and one of the hydrogens. Now I multiply these unshifted atom by the character which we have obtained by taking 3n vectors as the basis. So 4 into 3 is 12, 1 into 0 is 0, 2 into 1 is 2. So tau 3n is 12, 0, 2. So by this we have obtained this tau reducible directly. So like this we can have number of other examples. D4H point group, you can take the example of PTF, platinum tetrafluoride, and you can work out the examples for this. You can take number of examples. Now here till now we have taken the example of tau3n as the basis for representation. Now it is also possible I can directly use the bond vectors as the basis. Bond vector means like this, if I take any tetrahedral molecule, that is I can take tetrabromomethane. In this molecule it is a tetrahedral, and if I take this, how many bond vectors I am having? CBr1, CBr2, CBr3 and CBr4. I have 4 bond vectors, and I can make use these 4 bond vectors as the basis for representation. These bond vectors as the basis for representation is very, very important in further molecular application of this that we will see later on, that is bond stretching, etc. Now in this molecule, this is my C3 axis. This is my C3 axis, and these are my mirror planes. This is one, this is like this, and this is like this. So I have C3 along one of the carbon, and these are the base bromines, and this is the top bromines. So I am having C3 axis. How many such types of C3 axis you find? There are 4 C3 axis into this molecule. That is, if I put, this is another, if I put, this is another, like this molecule has those. Now in this model I will use 4 bond vectors as the basis for representation. C3 shifts bromine, these 3 bromine vectors, and it does not shift this because I am giving rotation about this, like this. Now, so by knowing this, I can also get the result directly. Now, here let me just take C3 operation. How many bond vectors are shifted? 3 bond vectors are shifted. This is not shifted. If I carry out one of the sigma like this, 2 bond vectors are not shifted, 2 are shifted. These are lying, these and these, they are lying into the mirror. So these are not shifted, and these are shifted. And now further, there is a rule that if the bond vector is shifted, it does not contribute character to the reducible representation. If the bond vector is not shifted, it will contribute +1 to the character. Thirdly, if the bond vector is not shifted, but only its direction is changed, then it will contribute -1 to this character, overall character of the molecule. Just by knowing this, I can go for the reducible representation for this directly. I have not to now multiply with the character corresponding to that. That is, I can directly get into this. So this is the tetrahedral molecules. In this text, I have just taken only the 3n Cartesian coordinates, and here I have just explained just by taking bond vector. Now let us take another example of the bond vectors where I am using this bond vector as the basis. That is, I will just take the example of bond vectors as the basis for representation. For this, let us take the example of CBr4 as shown over here in this. The C3 operation shifts all the 3 CBr bonds, only one CBr bond is not shifted. And we can work out now the character for this. Remaining effects can be worked out on this. What happens if I take sigma v like this? These and these will not change, this and these will change. So by carrying out C3 operation, 3 band vectors are shifted, 1 is unchanged, and by taking sigma V, 2 bond vectors are not shifted and 2 are shifted. And just by performing all other operations, we get the result as shown in the table. Unshifted vector, first column gives under E it is 4, under C3 it is 1, under C2 is 0, under S4 is 0, under sigma D it is 2. And tau bond vectors is given as 4, 1, 0, 0, 2. That is, here directly we multiply with directly the character. Now let us take another example, very common example of D3H point group. If I take PF5 molecules, there are 5 PF bond in it. If I take this, there are 5 PF bond into this molecule. This is my PF5 molecules like this. It has 5 bonds. One bond is this, one bond is this. These are axial bonds. Then these are equatorial bonds. So I am having 5 PF5 bonds. And I will see now the effect of symmetry operation of D3H point group. And for this, a figure is shown, and in which C3 axis together with C2 axis and sigma V. This is my C2 axis. It is like this. And sigma V is also like this. It is passing through this. So there are 3 sigma V's and 3 sigma 2. That is, this is my sigma 2. I can take this also as like this. So I am having sigma V, sigma 2 and C3 axis, and I will see the effect of symmetry operation on these 5 vector. This molecule also has sigma H, that is, this is my sigma H. All these 3 atoms, they lie into this plane. And now I will just see the effect of this. How? If I carry out this C3 rotation like this, these bond vectors, they are shifted and changed. These and these, they remain at the same place. Now what happens if I carry out C2 operation like this? This and this interchange, this and this interchange, only one is not shifted. Similarly, if I carry out this sigma, how many bonds are not shifted? This is not shifted, this is not shifted, and this is not. That is, I am having 3 these bond vectors which are not shifted, and these 2 are shifted. What about if I take sigma H? These 2 will be shifted and these 3 will not be shifted. So by performing the symmetry operation on this 5 PF bond, we get the various results which are shown into the table. Unshifted vector, they are given as, for E it is 5, for C3 it is 2, for C2 it is 1, for sigma H it is 3, for S3 it is 0, for sigma V is 3. And the tau bond vector, that is tau reducible, obtained by bond vector is 5, 2, 1, 3, 0 and 3. So just by taking this, we are having this.
Now, let us study base vectors xyz of unit length along xyz axis, which have been used for generation of reducible representation of a point group. One can use bond vectors for generating reducible representation. These types of representations are very important in dealing with vibrational spectra of molecules. Let us take few examples to explain this method of finding reducible representation. The first one to be discussed, there are 4 PTF bond vectors. To get characters for reducible representation for which PTF bond vectors are the basis, we have the following rules which will be helpful. The bond vectors which are shifted by the symmetry operation will contribute 0 to the character of reducible representation. The bond vectors which are not shifted contribute +1 to the character of reducible representation. The bond vector which is not shifted but only its direction is reversed will contribute -1 to the character of the reducible representation.
Now similarly I can make use of the p orbitals as the basis for finding tau reducible, d orbitals as the basis for finding reducible, and I can take ammonia molecule as an example again, and we can now reduce, we can find out what is the net result. That is just by noting down how many atoms are shifted, how many atoms are unshifted, and we know the character. If I take p orbitals as the basis, what is the character contributed? If I take the d orbitals as the basis, what is the character contributed to tau reducible? We can get the result for these also.
After studying this module, you must have clearly understood reducible representations for various point groups and various examples for this. You have also learned bond vectors as basis for finding reducible representations by taking various examples. P orbitals and d orbital function as basis for finding reducible representations with examples have also been discussed.
So, what we have learned in this module, how to generate reducible representation for various point groups by taking 3n coordinates as the basis and bond vectors as the basis for representation. I have taken the example of water molecule. I have taken the case of ammonia molecules, and we have seen how many atoms are unshifted, and later on by multiplying by the character for unshifted atom we get the tau reducible. Similarly, we have taken the bond vectors as the basis for finding reducible representations. An example I have taken that is that of carbon tetrabromide NPF5 molecules, and these we have seen how many bond vectors are shifted and how many bond vectors are not shifted. And by taking the rule under consideration, that is the bond vectors which are shifted contribute 0 to the overall character of the reducible representation. Bond vectors which are unshifted contribute chi is equal to +1 to the overall character of the reducible representation. Bond vectors which are unshifted but only direction is reversed contribute -1 to the overall character of reducible representations.